Start recording this now, and let me share this. Okay, so today's number theory. All right, we'll start looking at divisibility. So just the definition of divisibility to start with. If you have two integers a and b, we say that a divides b, or that a is a factor or a divisor of b, or equivalently that b is a multiple of a, if there exists some other integer c such that b is equal to a times c. Right? That's what we mean when we say a divides b. We say a divides b, basically if b is a multiple of a. And this is how we denote it. So a divides b. Now I've seen people write this the wrong way. If you put the b on this side and the a on this side, it means that b divides a, which is different. That means that a is a multiple of b. So make sure you get this notation correctly. If you want to do it the other way, if you want to say that b is a multiple of a, sometimes I've seen a similar notation to this, except we use a dotted line rather than a solid line. But we're not gonna use that, so I'll just use this notation for a divides b. Now, if a is not a if a is not a divisor of b, then just a line through it. So if we know that a is not a divisor of b, we could use this notation. Also note that a and b in this definition have to be integers. So for example, if I take, let's say a is 1.2 and b is 2.4, even though technically a, if you multiply a by 2, you get b, a and b aren't integers. So this definition doesn't apply there, right? And also, you have to be careful with the use of the word divides here. This doesn't mean that we actually literally dividing one by the other, right? It's different from that. This is just saying that, okay, if I multiply a by something, I'll get b. Right? We're not actually doing it. We're just saying that it can be done. And that's important when we come down to one of these things on here. All right, so for example, 2 divides 4, because 4 is a multiple of 2. 3 divides 15. And actually, minus 3 also divides 15, if you consider negative numbers. And 3 divides minus 15 as well. Right, the minus signs really matter when we're talking about divisibility. It still works. Now, these aren't true, right? So 5 is not a divisor of 18, and 6 is not a divisor of 9. They do have common divisors, but 6 itself doesn't divide 9. Because there's nothing you can, no integer you can multiply 6 by in order to get 9. Theorem 2 gives some basic divisibility properties that you should know, because these are standard things that you would use to solve any divisibility problem. The first 5 are really kind of straightforward. So start with every integer divides 0, right? Because if you take any integer and multiply it by 0, you get 0, right? So it means that basically 0 is a multiple of every integer. Now, if you reverse that, if you want to see what number satisfies 0 divided n, right? You need to multiply 0 by something to get n, and the only way that works is if n is 0. Right? So be careful with this one. This one means that the only integer that 0 divides is 0. It is not saying that 0 divided by 0 is a number, right? That's what I meant when you have to be careful with the definition here. We're not saying that we actually divided 0, and up here, we're not saying that, well, we're not saying that we actually divided something by 0. We're just using the definition of divisibility, which is different in this case. Okay, the third one and the fourth one are straightforward. So basically 1 divides everything because everything is a multiple of 1. And if you want a number to divide 1, that could only happen if the number itself is plus or minus 1. The fifth one is called the reflexive property. Basically, what you have there is that every integer divides itself, which is intuitive because if you divide any number by itself, you get 1. So every number is actually a multiple of itself. Now, from property 6 onwards, I want you all to actually prove these, right? So this is going to be homework for you all to prove properties 6 to 14. First of all, if you have an integer m divided n, and also n divides m, this is going to imply that m is equal to plus or minus n. And the way you do this, and actually the way you do most of these, is to use the definition of divisibility. So basically what you have is that if m divides n, it means there's an integer k1 such that n is k1 times m. Right? So n is k1 times m. From this one, you'll get m is k2 times n. Now you have to use different numbers because it's different divisibility statements. You can't use the same constant every time. So what you'll get is n is k1 m, m is k1, it is k2 n, and then you substitute for m into this one, and you will be substitute for n into this into one of them, and you'll get that essentially what you'll get is that something like m is equal to k1 k2 m, and then you could take cases either m has to be 0, or you would get that k1 k2 is 1, which means that k1 and k2 is plus or minus 1, and all of those cases would lead to this. So that you all can go through and try to write up a proper proof of it. The transitivity property is also important. So basically, if you have one integer dividing a second, and this second one divides a third, it means that the first must divide the third, right? And actually, this can be extended to any number. So if you had a fourth one, if this n, for example, divided q, it would mean that d divides q as well. The multiplication property, well, this basically says if you have a number, first number divided a second number, you could multiply both of those by any constant and the property still holds. So d times m would also divide d times n. Now the converse of this is only true when d is not 0, right? So if d is not 0, then the reverse holds. That's the 9th property down. And probably one of the most important of all of these is the linearity property we have here. Now, what it says is that if d divides two numbers, m and n, then d divides any linear combination of m and n. Now, a linear combination is basically where you take the first one, you multiply it by a number a, you take the second one, multiply it by a number b, and then you add that. So that's what we mean when we say a linear combination. So a multiple of m plus another multiple of n, where the multiples are linear, they're numbers. Right? And it doesn't matter what a is or what b is, as long as they are any integer, this divisibility would hold once these two hold. So when we're working with divisibility properties, this is one we use probably the most often. The linearity property. This one as well as the reflexive. The reflexive property might seem trivial, but it is used a lot. Right? The comparison property. Now, these here, well, yeah, these here are more intuitive, so they're easier to prove. So think about this one. If you have two positive numbers, so you have a positive divisor of a number, obviously that divisor has to be less than the number, right? Because you can't have a divisor, if they're both positive, you can't have a divisor being greater than n. If n was negative, then yeah, d would be greater, which is why we need to have the positive integers here. Right? And if d divides any integer n, it would also divide the magnitude. Right? It doesn't matter if we have a plus or minus sign, it would still work. Okay, and then the last, so here we have the magnitude of n is the largest positive integer that divides n once n is not 0. And last one, so you can think of this as if a divides m and b divides n, then you can multiply both. So a times b divides m times n, right? And this is true. Now, be careful with this. The multiplication one holds, but the addition one does not hold, right? So if a divides m, and b divides n, you can't add them. You can't say a plus b divides m plus n, because that doesn't work with divisibility. Okay, so just a note here, when we're working with divisibility statements, the idea is to use the available information together with all of these properties up here. Most often, you're going to use properties 5 and 10, like I said, the linearity and the reflexive. Now, for more complicated problems, the comparison property is actually pretty useful. Sometimes you could use this in situations where it actually simplifies the problem a lot, but it's not obvious that you need to use it. So always be on the lookout for this. And how you would use something like this is if you're trying to get a bound for the solution. So if you find out, basically, if you have things where you have one polynomial divides another kind of thing, you could try to create an inequality and then solve that inequality to get specific values of root, rather than checking all the values. So this would help you reduce the number of cases you have to check. Right, now how we use divisibility is like this. So suppose I wanted to solve something like this, right? I wanted to find all integers n that satisfy this divisibility statement. Basically, it says that n is a divisor of 3n squared plus 4. Now, it's not easy to see how to do that, right? Because you don't know what the divisors of 3n squared plus 4 are. If you know what they are, then you could try to take cases. On the other hand, if I had something like n divides 4, this is much easier to solve because I know what the divisors of 4 are, right? I just have to check plus or minus 1, plus or minus 2, and plus or minus 4. And basically, n could be any of those. Now, this here is actually equivalent to this. So if I could take this and go from here to here, then I could actually finish the problem and solve it. And you can do that using the linearity property and the reflexive property. So if you know that n divides 3n squared plus 4, it is also true that n divides itself. So I could use the linearity property, take this minus 3n times n, right? Basically, I'm trying to get rid of the n term. So I know n divides this. I know n divides 3n squared, right? And if it divides this and it divides 3n squared, it would divide a linear combination. So I could take this minus the 3n squared, cancel that, and you just get n divides 4. Right? This, what I just explained here, is not the same as what I had talked about with the addition here. So I hope that didn't confuse you. We're not adding two completely different divisibilities. Here it's the same number on one side. Right, and just a couple of examples here. So first one is find all integers n such that n divides n plus 1. Basically, what we have to do is find all integers where the number divides the number that comes, the integer that comes after. So basically, these are two consecutive integers. Right. So just like before, I could, if I take n divides n plus 1, I know n divides n, so I could subtract those and I'll get n divides 1. Right? And then from above, we know the only numbers that divide 1 are plus or minus 1. Right. Now, one thing to note is you can't stop here. You can't, once you get to this point, you can't stop here. You still have to verify that these work. The reason being is that what you've shown is that this statement implies that n could only be plus or minus 1. But you still have to show that if n is plus or minus 1, it actually holds. Right? Again, this is something with how you prove things. We started with this, and we showed that that implies this. But what you really want to do is find out integers n that actually satisfy this. And you don't actually know yet that these satisfy them. We know if it satisfies this, then it must be this. So now I have to say, well, if it's this, then yes, it satisfies them. So how you do that is, it's called verification. You basically take the values and substitute. So when n is 1, does it satisfy this? Does 1 divide 2? And the answer is yes. Right? So n is equal to 1 works. What about minus 1? If I have minus 1 and 0, does minus 1 divide 0? And the answer is yes, because again, based on the theorem before, If I multiply minus 1 by 0, I get 0. So minus 0 is a multiple of minus 1. Right? So both of these work in this case. Now, the next example illustrates why you need verification. Right? So similar question, except now we have 3n divides 5n squared plus 3. Okay, so if I want to do something similar, I'm going to use the linearity property here, right? So I have a is 3, b is minus 5n, and then I'm going to use the 5n squared plus 3 and 3n, basically this thing I have at the start. Again, the idea here is to get rid of any unknowns I have inside it on the right-hand side. Because if I get rid of the unknowns, I'll be left with a number. And then I could just consider the divisors of that number. So if I do this, I multiply this by 3 and I multiply this by 5n. When I subtract, it will cancel and I'll be left with 9. So I know that 3n divides 9, right? So I could simplify it like this, or I could just say, well, what are the divisors of 9? No, it's positive integers. So if n is positive, 3n is positive. So I don't have to consider negative here. All right, before it was just all integers, so I had negative to consider. So be careful with what the domain is. Anyway, so if 3n is 9, it basically means that n has to be, well, 3n has to either be 3 or 9. It can't be 1 because 3n is 1 doesn't give you an integer n. So only 3 or 9. And basically that means that n has to be 1 or 3. Now, if you didn't verify, if you stop here and say that 1 and 3 are the answers, then that's wrong, right? Because none of them actually work. So you have to verify that. Again, what we've done is show that this implies this, but we don't know yet that this implies that. So if n is 1, does that work? The answer is no, because 3 does not divide 8. When n is 3, 9 doesn't divide 40, so neither of those work. And that means that there's no solution in this case. All right, there are no values of n that work. Yeah.
It's really weird that like you're able to get to a point where you could, where you think you have solutions, but then when you check, they don't work. Is that because like the first statement you started with is wrong from the start?
Yeah, that is correct. It's because this thing is wrong. That's why there's no answers. And that is why verification is always important. You always check back.
Okay, cool.
Right? Because again, it's basically how statements work. So the reason why there's no solution is because, yes, you're correct, this is wrong. So if we start with something wrong and we get to this, it means that this only works if this is true, but this isn't actually true. So it actually doesn't work.
Right, yeah.
Yeah, so that's why I verify to make sure. Right, and again, I'm just going through this, but if you all have any questions at any point, please stop me and ask, because I'm assuming that you all understand what I'm saying, but just make sure that you do understand, right? Because now is the time to figure this thing out as we go. All right, so that's basic divisibility stuff. Now we go into slightly more complicated things, the division algorithm. So this is where we use divisibility now. So for any two integers, a and b, positive integers, it can be modified to work with negative as well, but we'll just consider positive for now. There exist unique integers q and r such that basically what it's saying is that this bq is the highest multiple of b less than a. Right, that's what we get. And r is basically between 0 and b. Right, it could be 0, but it can't be b. So if it's equal to 0, it means that b divides a. If b doesn't divide a, then r will be something that lies from 1 to to b minus 1. All right, remember these are integers. So instead of less than b, I could have put less than or equal to b minus 1. But again, that only works if it's integers. Now, the divisional algorithm is actually very useful. Not directly, you actually use it for other things. So it comes into the Euclidean algorithm later on. as well as other things like further on when we do Fermat's-Little theorem, some problems that you need to solve using Fermat's-Little theorem, you need to actually use the division algorithm first. Even though you're not actually saying you're using it. It's just, it's kind of like using it in practice. All right, so an example here, if I take A is 73 and B is 23, the highest multiple of 23 less than 73 would be 69. So that's 3 times 23. So I could write 73 is equal to 3 times 23, and then the remainder is 4. All right, and this thing here, this is actually, well, the division algorithm. This is very useful when we go into congruences later on, because that's basically what congruences are, right? Just the remainders. So here Q is 3 and R is 4. So this corollary here says that when you do this division, right, if basically D, well, in this case, I could say B would divide A if and only if R would be 0. So I just use different variables here. So D divides N if and only if the remainder is 0 when you divide it. This 0 here would be R. Okay, so it follows from the division algorithm that every integer can be written as either 2k or 2k plus 1. Right? Because the only possibility is if B is 2, right? If B is 2, then the only possibilities for R is either 0 or 1. So if B is 2, right? So it's 2q plus R, so it's either 2q plus 0 or 2q plus 1. All right, I'm just using k instead of q, basically. Right. Similarly, if you took B as 3, then the possibilities for R is 0, 1, or 2. So it's either 3m, 3m plus 1, 3m plus 2. I'm using different variables so you don't think it's the same variable each time, right? And then you can continue like that. If you wanted for 4, every integer is either 4n, 4n plus 1, 4n plus 2, or 4n plus 3. Now, one thing I want to note here is that sometimes it's actually easier to use negative instead of plus. So I have here 3m plus 3m, 3m plus 1, and 3m plus 2. This 3m plus 2 can also be written as 3m minus 1. And when you have to do things like add these together, right, it's actually easier to take the minus 1 instead of the plus 2, because when you take the minus 1, it'll cancel. So things like arithmetic progressions and things like that, you usually consider the case where you have the negative ones because things cancel easily. All right, so just repeat that this 3m plus 2 could also be written as 3m minus 1 and it's so whole. Basically, you take this and instead of taking the number that comes after this, you take the number that comes before this one, and it so works. Because these are really just 3 consecutive numbers. Similarly, these are 4 consecutive numbers. So I could have taken 4n minus 1 instead of this, right? Doesn't make sense to go 4n minus 2 because then you're canceling the 4n plus 2, which, I mean, you could do it if you want to. All right, I'm not going to go through the exercise questions. Did anybody have any questions about this? Or anything in this you want me to explain? Okay, good. Oh, and well, you all have the hints / solutions, so you can go through those as well. And if you have any issues, you can ask. Okay, so the next main section is GCD and LCM, primarily GCD. That's the more important one. Like I said previously, the GCD, greatest common divisor, is basically the same as the highest common factor. They mean the same thing. I know you all might be more familiar with the term highest common factor. That's the one you learned probably in primary school. All right, so the greatest common divisor is basically, as the name implies, it's the highest number that divides both of them. Right, the biggest number that divides both of them. Now, by convention, I had if you have a number and 0, a positive number and 0, the GCD would be the positive number. Right, you could extend that to any number. So if you take the GCD at 3 numbers, it would be the highest number that divides all 3 numbers. Now, when you're talking about GCD with more than 2 numbers, you have to be careful because you could either be talking about mutual GCD, which is basically like this. where you take all the numbers together and then the GCD is the one that divides all, or you could be talking about pairwise GCD, which is basically the GCD of E1 and E2, and the GCD of E1 and E3, and then the GCD of E2 and E3. Those are separate, so it's GCD for each one. So you have to be careful what things are done. Right, some examples here, I wouldn't go through those, straightforward. This definition is important. So two things are relatively prime if the highest number that divides both of them is 1. Basically, they have no common prime divisors. All right, and then the lowest common multiple, the LCM, is just the largest number that is a multiple, sorry, the smallest number that is a multiple of both of them. All right, so for example, the LCM of 4 and 6 would be 12. 12 is the smallest number that is a multiple of both 4 and 6. All right, now this part, I'm not going to go through in detail like I did with divisibility, because a lot of these are similar ideas to what we talked about with divisibility. Is there anything in here that you're all a little confused by that you want me to explain? If not, I'll just skip this part. Okay, good. Some of these you do have to like think about a little bit, but they work out in the end. Right, so if I wanted to find the GCD of these two numbers, again, the idea is the same as with divisibility. You could do it like this, or you could say D, if you want to find let the GCD be D, and you're saying that D divides this, D divides that, and you can count, get rid of the ends, find the number that D divides, and then you try to see if the largest one of those wins, because it's GCD, which is the highest one. So you could try it that way as well and see what happens. Now, using the GCD properties, if it divides this and it divides that, it could divide this minus that, right? Which would be n minus 2. And then it would divide that minus that, which is n plus 5. And then it would divide this minus this, which would be 7. And you always keep the lowest, the smallest one as you go, because you don't want to keep the largest one. The idea is to try to simplify it as much as possible. Now, once you get to the GCD of two things, and one of those two things is a number, then the GCD must be a divisor of that number. So it's either 1 or 7. Right? And then at this case, at this point, you have to verify as well, just as before. So you check to see if 1 or 7 can work. Right? And now this time is different, right? So when you check in 1 or 7, you're basically trying to find values of n that will give you 1 or 7. Right? It's not substituting 1 or 7 directly. So you actually have to, this is a little trial and error compared to before. So in this case, it's easy because n is 1 and 2 will automatically give you the answers. Sometimes you might have to try different values like n is 5 or something like that to get something that works. All right, so when n is 1, the numbers become 4 and 5, which are relatively prime, so GCD is 1. When it's 2, you get the same number, 7. So automatically the GCD is 7 works. Therefore, these are the possible values. Now, there's an example I want to show you that uses GCD, right? Because there's one technique where you can use the GCD where it's not mentioned anywhere to help you solve the problem. So in the miscellaneous exercise in the same section on number theory, question 11 is a question here. Find all triplets x, y, and p of positive integers where p is prime. So x and y are positive integers, p is prime. And they satisfy this. Now, it's not stated anywhere. There's nothing about GCD in this question, right? But you could use the GCD to help you solve it. And this is how you would introduce the GCD in a question. This is the solution now here. So if you let the GCD of x and y, in this case, p is by itself, so we'll leave p for now. We'll just consider x and y. So let the GCD of x and y be d. And if the GCD of x and y is d, it means that x is d times something, so I'll call that something a, and y is d times something else, I'll call that b. Right, so I could write x is dA, y is dB. Now, because d is the GCD, it means that a and b have to be relatively prime. Because if they had a common factor, then D wouldn't be the GCD. There would be something higher than D dividing both of them. Right? So once you do this, automatically the GCD of A and B is 1. Now, one thing to note, if the GCD of A and B is 1, then if I add A to this, right, doesn't affect the GCD. So the GCD of A and A plus B is also 1. Similarly, the GCD of B and A plus B is also 1. Right? Because if something divided both of these, it divides B and it divides B, so it would also divide A plus B. Well, sorry, it divides A plus B and it divides B, so you divide the difference, which means it would divide A and you will get a contradiction. Okay, so what we're going to do is substitute these two. Substitute X and Y as these things in here, right? And you get this. After you simplify, so you cancel as many D's as you want. One of the D's will cancel from the denominator, one will cancel. Now, the reason why GCD is important here is because now A and B are relatively prime, right? So I know A plus B, well, on the right-hand side, I have P, which is an integer. So the left-hand side must also be an integer. Right, so this is an integer, which means that A plus B has to divide this. So forget about D for now. This B cubed, well, let me come back to this one. So I have the GCD of B and A plus B is 1. If there's no common prime divisor of B and A plus B, it means that there's no common prime divisor of B cubed and A plus B, right? Because if I multiply this by itself 2 times, then it doesn't change the fact that the GCD is still 1. So this B cubed is relatively prime to this. So this doesn't divide this, which means that this has to divide everything else here. Actually, it doesn't divide A, so it has to divide D cubed, but we're not concerned with that right now. The fact is that A plus B doesn't divide B cubed. So I could write this outside in brackets, and this equation would still be valid, and then the D cubed A over A plus B has to be an integer. But the point I'm trying to make here is that if the prime number P is equal to all of the product of those, and we have an integer times B cubed, it means that B cubed is a divisor of P. But P is prime. So it means that B cubed could only be 1, right? It's positive, so it can't be minus 1. So that forces B to be 1. And that's how we actually simplify the problem using the GCD. Because if we did not introduce the GCD, we would not have been able to do this. Right? Because the GCD is actually what helps us. The fact that this has to divide the GCD cube. All right, so using B is 1, I substitute that and then rearrange, basically carry the A plus 1 across on the side, multiply, and then bring the AP back on the side and factorize. All right, now again, P is prime, product of 2 things is a prime, so either A is 1 and this thing is P, right? I would give you D cubed is 2P, which is a contradiction because, well, I have a prime number times 2. That could never be a cube, right? And then the only other case is where A is equal to P and this is equal to 1, right? And then when you solve, you'll get A is D cubed minus 1, which you can factorize, right? And again, P is a prime number. So either this is 1 or this is 1. It's impossible for this to be 1, so this one has to be 1, which gives you D is 2, and P works out to be 7. Right, so that's basically it, the only solution here. So I just wanted to show you this to show you how the GCD can be used in a problem. All right, I think we'll have to pause here and then continue in a few minutes because I think we're going to get locked out now. So let me stop sharing this.